Good day, students. In this clip, we're going to be going over some examples on the application of exponents and logarithms. Um, the applications mainly. All right, so let's go ahead and take a look at the formulas first before we do some examples. All right, so let's take a look at the formulas. All right, so we're going to look at the discrete growth first. So write this down, discrete growth or decay. Now, when I say discrete, it means the growth happens per period, like every year, every month. There's some kind of compounding going on. Okay, it's not continuous. Something that's not continuous is discrete. So if you have discrete growth or decay, the formula is given by y equals y sub 0, the original amount, times 1 plus or minus, plus is for growth, minus is for decay, 1 plus or minus the growth rate raised to the t power. Okay, now this formula is for is if the growth is happening once per growth period, or in most cases once per year. So in this case, this is once per period. Okay, so whatever period the growth rate is determined in written in terms of, that's what will happen. Let's say if it's a year, it'll be once a year. You know, if it's a month, it'll be once per month. So whatever time period the growth rate applies to. But if it is more than once, if it's compounded more than once per period, the formula is going to be y equals y sub 0, the original amount, times 1 plus or minus, plus for growth, minus for decay, 1 plus or minus the growth rate over the number of times it's compounded in that period, raised to the t times n times, let's write it nt, because n comes before t, raised to the nt. Okay, this is a formula if it was compounded n times a period, n times per period. All right, so this is the formula for, or these are the formulas for discrete growth and decay. Okay, now what if the growth were continuous? What are the formulas for those? So continuous growth or decay, that one can simply be given by y equals y sub 0, the initial amount, times e raised to the kt. Okay, in this case, k is a growth constant for your model. All right, now let's take a look at question number 1. Question 1, it says, there's a depreciation problem. It says the car is worth $25,000 when it was bought. It depreciates at a rate of 7% per year. When will its value be $15,000? We can clearly see that the growth rate here is going to be negative. So the formula we're going to be using here is y equals y sub 0 times 1 minus, because it's a decay problem, okay? 1 minus the growth rate in decimal form raised to the t power, okay? All right, so let's populate our, indicate what our variables are, so we can plug it into the formula, okay? So y sub 0, what is y sub 0? Let's indicate what it means first. Initial amount, initial value. In this case, it's 25,000. R is the depreciation rate. It's 7%. 7% is 7 over 100, right? So that basically means you have to move the decimal point forward twice to convert it into decimal form. Well, that's what you always do, so it's 0.07. Okay, don't forget to move your decimal point forward twice on the bottom, and then at the top, move it forward twice. Okay, so it's going to be 0.07. All right, so that's the growth rate. T is a time period that we're looking at how much the car depreciated by. In this case, we do not know. That's what we're looking for. And then y is the final amount, final value. after depreciated for a t period of time. In this case, the final value is $15,000. Okay. All right, let's plug in these values into our formula and calculate what the time period for this depreciation is. Okay, so plugging it into the formula we have up there, we have 15,000 equals 25,000 times 1 minus 0.07 raised to the t power. Okay, so we can divide both sides by 25,000. Remember, the goal is to get t by itself. All right, on the right side, the 25,000 is divided out. And we have, so we're going to have 1 minus 0.07 is 0.93 to the t power. And on this side, can cancel out the zeros. 5 goes into 15, 3 times 5 goes into 25, 5 times. All right, so to get bring down t, we take the natural logarithm of both sides. So natural logarithm of 3 over 5 equals a natural logarithm of 0.93. All right, so we use the power property of logarithms to power down this exponent, this variable exponent that comes down here. So this equation is going to become the natural logarithm of 3 over 5 equals t times the natural logarithm of 0.93. Okay, and then to finish this up, we'll divide both sides by the natural logarithm of 0.93. That is by the natural logarithm of 0.93, and divide this by the natural logarithm of 0.93. All right, so t is going to be what you get in your calculator when you plug in this this ratio right here. Okay, so we get our calculators. We're going to compute the natural logarithm of 3 over 5 divided by the natural logarithm of 0.93. All right, and the answer is 7.039, or approximately 7.04. So t is equal to 7.04 years. All right, so let's write down what the meaning of our answer is. So it will take 7.04 years for the value of the car to depreciate from 25,000 to $15,000. Okay, so there you have it. All right, let's take a look at question number 2. Question 2 has to do with investing. It reads, you invest 5,000 in a fund that yields 7% a year. How long will it take to double your money if your interest is compounded annually? And let me add another piece to it. For the same time frame, how much would your asset grow if your interest was compounded monthly? Okay, so for the first part, let's call it the A part. We're going to find out how long it takes for you to double your money. All right, so this is discrete growth. So we're going to be using the formula y equals y sub 0 times 1 plus r to the t. Okay, because for the A part is compounded once per year, so it's just once per period. Okay, so let's label what we know and need to find. Y sub 0 is the original amount, which is 5,000. Y is the final amount, which is double the initial amount. So double y sub 0. Doubling y sub 0 basically means you're doubling 5,000, which is 10,000. So we're looking for when you'll be able to hit this amount. The growth rate is 7%. 7% is 7 over 100. Converted into decimal form is going to be 0.07. And the time is how long does it take for You have money to double. That's what we're looking for. We don't know what that is, okay? So I'm going to plug all these pieces of information into our formula for calculating exponential growth. And then we're going to determine what t is, okay? So we have 10,000 as y equals 5,000 for y sub 0 times 1 plus 0.07 raised to the t, okay? Now we can go ahead and divide both sides by 5,000. The left and right side divided by 5,000. And then we're going to have 2 equals 1.07 raised to the t power. All right, so to power down this exponent, we're going to make use of the logarithm. We're going to take the logarithm, natural logarithm of both sides. So natural logarithm of 2 equals a natural logarithm of 1.07 to the t. Okay, so using the exponential property of logarithm, we can power down this exponent. So we'll have natural logarithm of 2 equals t times the natural logarithm of 1.07. So to finish this up, we'll simply divide both sides by the natural logarithm of 1.07. So natural logarithm of 1.07 and divide this by a natural logarithm of 1.07. All right, this divides out. So we're going to have t equals, now we're going to plug that into our calculators. So we're going to do, let's see, the natural logarithm, let's do that again, the natural logarithm of 2 divided by the natural logarithm of, keep bringing something else up, the natural logarithm of 1.07, and the answer is 10.24, rounded to 2 decimal places. So 10.24 years will be how long it takes for our money to double. So it's 10.24 years. Okay, so let's write down the meaning of the answer for the A part. It takes 10.24 years for your money to double. Okay, to double basically means for it to go from 5,000 to 10,000. So for the B part, if it's compounded monthly for this time period, how much will you have after 10.24 years? So we're going to use a formula y equals y sub 0 times 1 plus r over n raised to the nt. Okay? All right, so let's see what we have here. So the starting amount, y sub 0, is 5,000. The growth rate is still 7%, which is the same thing as 0.07 in decimal form. The time is 10.24, because we're referring to the same time frame. And then let's see, n is how many times it was compounded in a year. How many months are there in a year? So you have 12 months in a year, so if it's compounded monthly, there'll be 12 times that it'll be compounded, okay? And then y, we do not know what it is. All right, so let's populate our formula with these values and see how much you have for that time period if you're compounding it monthly. Okay, so we're going to have y equals 5,000 times 1 plus 0.07 over 12 raised to the 12 times t, which is 10.24. Okay, we can plug in this whole expression in our calculator and just determine what the whole thing is in one step. So let's go ahead and do that. So we're going to do 5,000 times 1 plus, I'm going to group this fraction in parentheses so I don't get confused. So we're going to put in 0.07 divided by 12. Close that, close that. Now we're going to raise this expression in the parentheses to the parentheses 12 times 10.24 power. Press enter. All right, let's go over our pretty prints to make sure that our entry is consistent with this expression we have right here. So we have 5,000 times 1 plus 0.07 over 12 raised to the 12 times 0.24. Excellent. So you notice that our amount is going to be $10,218. So let's see. Final amount is y is $10,218. Okay. So let's write out the meaning of this answer. The final amount after 10.24 years, if the interest is compounded monthly, it's compounded monthly, is $10,218. Okay, so you can clearly see that if your interest is compounded monthly, it grows quicker than if it's compounded once a year. All right, so there you have it. All right, let's take a look at question number 3. It's a half-life calculation. It says the half-life of californium-251 is 898 years. First of all, find the decay constant of this radioactive isotope. And then after doing that, if you have 150 grams originally, write the decay model for the amount left after t years. And then for the C part, use your model to determine the amount left after 100 years. Okay? So part 1, we want to find what the decay constant is. All right, so when we're dealing with radioactive decay, that process happens continuously. So we have to use the equation y equals y sub 0 times e to the negative kt. This negative is because we have a decay situation here. Decay means there's a reduction in amount, okay? All right, so let's see what we have. The initial amount, generally speaking, we're not given any initial amount, so y sub 0 is the initial amount. The final amount, we know that it's half of the original amount because we deal with half-life situation here, so it's half of the original y sub 0. The decay constant k, we do not know what it is. That's what we're looking for. And then the time is 898 years. All right, so let's input these values into our decay formula and determine how long it takes for half of an original amount of californium-251 to decay, okay? All right, so let's put it in. We will have 1/2 y sub 0 equals y sub 0 e to the negative 898t. All right, so first thing we'll do, divide both sides by y sub 0. Remember, the goal is to isolate y sub 0 is to isolate k. So I made a mistake here. Let me fix that. 898k, because t is 898, so let's change that to k. All right, so this divides out. The y sub 0 divide out, divide out, divide out. So we'll have 1/2 equals e to the negative 898k. So to get k isolated, we have to power it down, but we need to take the logarithm, natural logarithm of both sides first, in order for us to do that. So we'll take the natural logarithm of 1/2 equals the natural logarithm of e to the negative 898k. Okay, so on the left side, we still have natural logarithm of 1/2. And natural logarithm and e, they are inverses, so they cancel each other out. So we're left with negative 898k. So to get k isolated, we divide both sides by 898, negative 898, and this by negative 898. So that yields k equals, let's plug this into our calculator. Let's see. The natural logarithm of 1/2 divided by negative 800 and let's see what's going on here. All right, divided by negative 898. This is the exact answer. We need an approximation, so diamond enter 0.0072772, 0.00772. Okay, so our decay constant here is 0.000772, negative. Okay, all right, so there goes our decay constant. So let's write down what this means. The decay constant of Californium 251 is negative 0.000772. Okay. All right. So for the B part, we have to generate a model if you had an initial amount of 150 grams. So here we have the initial amount is 150 grams. We want to write a model using this formula, y sub 0 e to the negative kt. So let's see what we have here. The decay constant is negative 0.000772. The time is t. We're just writing down the model. The final amount we do not know. Okay. So the decay model is going to be decay model. It's pretty straightforward. It's simply the function that helps us to generate the remaining amount after a t period of time. Okay, so y is equal to y sub 0 e, well actually is 150 in this case. So about that, 150 y sub 0 e to the negative 0.000772 t. So there goes your decay model. Okay, so what we're asked to do now is we're asked to use this model to find. We have to use this model to find how much amount. What's the amount left after? Let's see. Let's go back there. After 100 years. Okay, after 100 years. So all we are doing here is calculating the final amount when t is equal to 100. So for c, y is going to be 150 e to the negative 0.000772 times 100. Okay, we just simply plug this into a calculator to figure out the amount. So let's move this to the side. We're going to have 150 times e to the negative 0.000772 multiplied by 100. Close the parentheses, enter. So you have 138.886 grams left. Okay, to 2 decimal places, we have 138. Let's leave it to 3 decimal places. So it's going to be 138.856 grams. So 138.856 grams. All right. So there you have it. Now let's write down what this answer means. What does this answer mean? It means that after 100 years, you will be left with 138.856 grams of Californium 251. Okay, so there you have it. But thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel by clicking up here for more updates and cool calculus clips such as this. And please post a comment to let me know what you think about this presentation. More clips can be found on math.serve.com/calculus, so you can click on this QR code for direct access to this website. Now, to demonstrate mastery of the examples we just did, why don't you take a look at example 4, try this out on your own, and post a comment, post your answers, let me see if you got it or not, and if you have any questions, you can always post a comment. Thanks again for watching, and have a wonderful day.